Okay, welcome back to part 2 of energy stores and transfer. In this part of the video, we will be covering about principle conservation of energy and how do we apply it in questions. Okay, so over here you can see that if I were to light up a matchstick, okay, the chemical potential store of the matchstick will be transferred by heating to the internal store of the surrounding. If there is originally 20 joules of energy in the chemical potential store of the match heat, all these 20 joules will be transferred to the internal stores of the surrounding. Okay, you will see that no matter how much energy I have at the start, I will always have the same amount of energy at the end. Okay, so it comes to the principle of conservation of energy, which states that energy cannot be created or destroyed, but it can be transferred from one store to another, and the total energy of an isolated system remains constant. Okay, the word system must be present because we say that we don't say that total energy remains constant, but total energy of the system remains constant. With regards to what is a system, it can be anything. It can be just one object, or the object and the surrounding can also be a system. Depends on what you define as the system. Okay, so let's take a look at an example of an ideal pendulum. Okay, initially the pendulum is lifted to a position of A, so it's slightly above the ground. There is gravitational potential store. As the pendulum swings, okay, energy from the gravitational potential store will be transferred to kinetic store at its lowest point, where it doesn't have a height above the ground. So everything will be converted to kinetic store, and then it will continue to swing up again. Okay, in an ideal pendulum case, there is no energy lost to the surrounding, or the kinetic store will again be transferred or to the gravitational potential store in C. So if I were to look at a system, okay, like an ideal pendulum in this case, originally is GPE. I have 1, 2, 3, 4, 5 units of gravitational potential store. Okay, it will all be transferred mechanically into kinetic store as the pendulum swings. Okay, and then eventually when the pendulum swings from the bottom position, B to C, all the kinetic store, 5 bars, will all be transferred to gravitational potential store, and the pendulum should reach the same original height. Okay, so you see kinetic energy become GPE. That is for an ideal pendulum. Okay, but if there is air resistance, that means it's not an ideal pendulum. There will be some energy loss because of air resistance as the pendulum swings. So whenever there is air resistance, this is what's going to happen. Initially, I have gravitational potential store, 10 joules, okay, at position A. As it swings towards B, energy gets transferred mechanically to the kinetic store, but my kinetic store will no longer be 10 joules. It will only be 8 joules because some of the energy gets out of the system, out of the pendulum, okay, but heat as heat, so it goes as internal store of the pendulum as well as the surrounding. The pendulum and the surrounding get slightly hotter because energy is being lost due to air resistance. So I have 2 joules being lost due to air resistance. Okay, then similarly, when from B to C, okay, I will again lose 2 joules of energy to the internal stores of the surrounding and to the pendulum as I continue to swing from B to C. So eventually, when I reach C, I will only be left with a gravitational potential store of 6 joules instead of the original 10 joules. So you'll see that the pendulum bob will reach a lower height because I have lower gravitational potential store of 6 joules now. Okay, so there is a continuous dissipation of energy to the internal stores of the pendulum and the surrounding. So the height reached by the pendulum decreases. And eventually, if this process were to continue, the pendulum bob will eventually come to a stop. So by considering the pendulum and the surrounding as a system, the total amount of energy in the energy stores of the pendulum bob and the surrounding remains constant. Okay, there is no energy loss because energy is just to get transferred to the surrounding. But if the surrounding and the pendulum is the system, So again, total energy will always remain constant at 10 joules in the above example just now. Okay, so let's take a look at this concept cartoon. Okay, there is a robot over here. You may pause the video to think about who is correct, whether A, B, or C is correct. Okay, I'm going to go through now. The correct answer is actually the lady over here, C. It says that the energy in the chemical potential store, in this case, is via batteries or electrical means, is transferred electrically to the kinetic store of the robot as the robot moves. Okay, and the kinetic store of the food tray because the food tray moves together with the robot, and the internal stores of the light in the robot. Okay, so based on principle of conservation of energy, energy can be created or destroyed, so energy cannot be used up. So the first person is wrong, which says that the energy in the chemical potential store will be used up gradually as the robot moves around. So yes, the battery will die off, okay, but it's not being used up. It's being used to convert into KE as well as internal stores. Okay, then what happens for B? B is wrong because as the robot moves across the floor, there is no change in gravitational potential store of the food tray. The food tray is just maintained at a constant height. Okay, so B is wrong because it says that the energy in the chemical potential store is transferred electrically to the kinetic store of the robot and the gravitational potential store of the food tray. But the food tray did not get tired. Okay, so the last answer is correct. Okay, the flow of the electric current will increase the temperature of the filament wire of the light bulbs, and this causes the light bulb to light up. So energy is transferred from the lights of the robot to the surrounding as well by electromagnetic waves. So we zoom into more work examples now. Okay, so in this case, I have a ball of 500 grams. It's being dropped from a height of 10 meters. What is its initial energy in gravitational potential store? And determine its velocity just before it hits the ground. Whenever we are faced with questions, it's best to draw a diagram to visualize it. That's the first step of problem solving. Okay, so I will draw a very simple diagram that looks like this, and I will put down all the things that is given, all the important variables that is given in the question. So over here, I have 500 grams ball is being dropped down a height of 10 meters. Okay, so this is what the question gives me. So in my head, okay, the purple one is what I should be thinking about. Oh, so the ball is initially at a height of 10 meters. Okay, so the ball initially have gravitational potential energy, GPE. And as it drops down, it is actually transferred to kinetic store. So there is kinetic energy when it reaches the bottom. There is no longer GPE because there is no longer height. So at the bottom, it's all converted into kinetic energy, which is given by the formula half mv squared. This purple part is the second step of problem solving, is whether you are able to link, okay, whatever things that is given into the questions to the concept that you have learned. Okay, then after that, we apply it. Okay, if you are able to link it, you should be able to know your content knowledge about the formulas mgh and half mv squared. You should be able to get the initial one, 500 grams, changed to kg will be 0.5 kg times 10 times 10, you get 50 joules. So initially, I have 50 joules of energy. This 50 joules of energy will all be converted into kinetic energy in the kinetic store. So half mv squared will be 50 joules. So I will just sub in all the numbers and I square root it. I get the velocity, which is 14.1 meters per second. Okay, next. The same question, a ball of 500 grams is again dropped from a height of 10 meters, but now there is an energy loss of 10 joules due to air resistance. Determine its velocity just before it hits the ground. Again, I'm going to draw my diagram. 500 grams ball is dropping down. Okay, so again, GPE is being converted into KE, but in this case, I'm going to draw an arrow out. Okay, as I transfer from gravitational potential store into kinetic store, 10 joules of energy gets lost. So I have an arrow of 10 joules. So originally, I should have 50 joules, okay, as calculated initially. But as I drop down, I actually lost 10 joules. So I'm only left with 40 joules of kinetic energy at the end. And then I want to find its velocity. So I just equate half mv squared to 40 joules. And then I sub in. So now my speed will only be 12.6 meters per second. Okay, so the last step of problem solving is to check that your answers make sense. So it does make sense because there's energy loss. So my speed will be lesser because I will have lesser kinetic store, okay, as compared to the first scenario, whereby it's 14.1 and now my velocity is only 12.6. Okay, next work example. A 500 grams ball is being thrown vertically downwards. So when you throw the ball downwards, you are exerting a force on the ball. Okay, you don't drop the ball from rest. So I exert a force to push this ball downwards, okay, from a height of 10 meters with a velocity of 5 meters per second. It hits the ground and bounces. It then rises to a maximum height of 8 meters. Determine the energy lost at the bounce, assuming no energy is being lost due to air resistance. So again, the first step is to draw a diagram. So I will draw my diagram like this. Okay, 500 grams ball initially has a speed of 5 meters per second. So I'm going to put down everything that is important in the question. Okay, after I draw my diagram, label everything that is important. So it drops down to a height of 10 meters and then it's going to bounce up to a height of 8 meters. Okay, so this is my diagram that I get from my question. I have input all the variables that is needed. Okay, so next step is the thinking step about what you have learned in your theory. Okay, you should be able to get that why is there an energy loss? Because the height of the ball decreases. It goes from 10 meters to 8 meters. Okay, so energy is lost as the ball cannot reach back a height of 10 meters. If the ball can bounce back up to a height of 10 meters, that means that there is no energy loss during the process. But since I can only bounce up to 8 meters instead of 10 meters, there must be some energy loss. Then the next step is you should be able to identify what are the types of energy at the start. So at the start, I'm at a height of 10 meters, I have gravitational potential energy. And then I am not being dropped down from rest. Okay, I do have a speed at the start because the ball is being thrown downwards. So there is a speed of 5. So there is gravitational potential energy as well as kinetic energy right at the start. At the end, okay, when the ball reaches its maximum height, it bounces up to its maximum height at 8 meters. The ball will stop momentarily before it starts to drop down at the maximum height. So there is no more kinetic energy at this part. There is only gravitational potential energy. So if I want to find the energy loss, I only need to find the energy at the start minus away the energy at the end. I get the amount of energy loss. Okay, so initially, I have kinetic plus gravitational potential store. At the end, I don't have any kinetic, it's 0. I have potential store plus energy loss. Okay, so if you were to sub in, you should be able to get 16.3 joules of energy loss. Next, if the speed of a springboard diver decreases by half on entering the water, by how much will his kinetic energy decrease? Okay, so when the speed drops, how much will the kinetic energy decrease? You should know kinetic energy is linked to speed by the formula half mv squared. Okay, so the initial kinetic energy will be half mv squared. And then as he enters the water, the final kinetic energy will be half m, and then the v will be half of v squared. Okay, so if you were to open up this, because the speed is being squared and you have half of the speed, okay, you are actually having 1/4 of the speed. 1/4. Half v squared will be 1/4 v squared. Okay, so the final kinetic energy will only be 1/4 of the original kinetic energy. Okay, 1/4 of the original kinetic energy, but I didn't ask for how much is the final kinetic energy. I asked for how much will the kinetic energy decrease. So initially I have half mv squared. At the end, I have 1/4 of half mv squared. So I would have the kinetic store would have decreased by 3/4, not by 1/4. 1/4 is the final one. So the kinetic store decreases by 3/4. Okay, let's move on to the next question. Over here, I have a roller coaster. Okay, I have five sections. Okay, you are supposed to pause the video and think about how does the energy store varies along these 5 different positions. Okay, so I'm going to go through now. Okay, what I do is I look at the gravitational potential store. Okay, the gravitational potential energy. At the higher it goes, the higher the gravitational potential energy. Okay, so this will be my answer. At position 1, I'm the highest height, so I have the highest gravitational potential energy, which is 4,000 joules. As I goes down, this is the second highest height, so I'll be 3,000 joules. And then at the lowest point, I don't have any gravitational potential store. It will be 0 joules, so it's number 5. And then next, I'll increase slightly to 1,000 joules, which is number 2. And lastly, I'll reach a even higher height, okay, which is 2,000 joules. 4. Okay, if you notice a trend, the total amount of energy at 13524 will always be equals to 4,000 joules, but it's just converted between gravitational potential energy as well as kinetic energy. But the total amount of energy will always be 4,000. So it's 4,000 plus 0, 1,000 plus 3,000, 3,000 plus 1,000, 2,000 plus 2,000, and 4,000 plus 0. Okay, the total energy will always be the same at 4,000 joules. Okay, so that's it for this section.